Hi, this is Kevin from Mathsaurus, and in this video we're going to look at the solutions to questions 16 to 20 of the Junior Kangaroo paper from 2019. That's the follow-on round from the Junior Maths Challenge for students that have done really well in that paper. But I actually don't think you should watch this video because I've taken all of the questions from the Junior Kangaroo from 2019 as well as the Junior Olympiad from 2019 and put them into a totally free online course. So you can go over to that online course by clicking the link in the description below, and you can work through all of these questions one at a time and then watch my video solutions. I've also got a totally free course over there going through the Junior Maths Challenges from 2020 and 2021 if you haven't already seen that, and I'll put that in that link in the description below as well. If you haven't already taken the Junior Maths Challenge, the best place to start would be with the Junior Maths Challenge papers and then go on to the Kangaroo and the Olympiad papers once you're ready for them. In question 16 we've got 8 cards numbered from 1 to 8 placed in 2 boxes P and Q. So the sum of the numbers on the 3 cards in box P is equal to the sum of the 5 cards in box Q. Which of the following statements must be true? Okay, so I've got box P here that has 3 cards in it and box Q that has 5 cards in it, and somewhere between these they've got the numbers 1 to 8 in them. Now, because the totals are the same in both, it makes sense here to think about what the overall total here is. 1 plus 2 plus 3 plus 4 plus 5 plus 6 plus 7 plus 8. If you add those together we get 3, 6, 10, 15, 21, 28, 36. By the way, adding these sorts of numbers together comes up a lot, and as you're getting really good at maths challenges you might just want to remember the sum for the formula for the triangular numbers. This is one of the things that I talk about in the Go for Gold in Maths Challenges course that I've got that I'll link below as well. But if you want to sum the numbers up to n, so if n is 8 here, you just do n times n plus 1 and then divide it by 2. So here you get 8 times 9 over 2, which is the same as 9 times 4, which is 36. Can be a handy little formula to have up your sleeve. Anyway, if the total is 36 and it's the totals are equal in P as in Q, that means these 3 cards have to add up to 18 and these 5 cards have to add up to 18. So let's look at the 3 cards, that's the sort of more restrictive one somehow, and see how I can get 3 to add up to 18. So I'm going to be probably using the larger numbers if I've got fewer cards here, right? So I could do 8 and 7, that's the biggest choices I've got. That would add up to 15, and then I'd have a 3, which would take me to 18. So I'm going to do this systematically. Actually, systematic listing is also in that other course that I just mentioned, and it's a skill that's really useful. But by systematically I mean I'm just going to start here with the biggest possible numbers and then work my way down until I run out of options. So I could keep the 8 and then have a 6, and that would be 14. That would leave me with 4. If I tried to do 8 and 5, that would be 13, so I'd need another 5 to get to 18, but there's only one 5, so I can't do that. And as soon as I get down to 8 and 4, well, it's the same option that I've already done, 8, 6, 4, right? So I don't need to keep going with those. I could get rid of the 8, and I could start with 7. The biggest number that can go with that is a 6, so that's 13, and then I've got 5 left over, which takes me up to 18. And again, you can see, okay, as soon as I go down to 7, 5, well, I'm just going to get the same combination again, and you know, I can't do it with just 6 or less. That doesn't get me to 18. So they're the only 3 options here. And then I can just write down the other numbers that are not here. So if I just miss 3, 7, and 8 out, I'm going to have 1, 2, 4, 5, and 6. We know they must add up to give 18 by the way we've done this. And in the second case, it would be 1, 2, 3, 5, and 7. And in the last case, it would be 1, 2, 3, 4, and 8. So I can just look at these statements now and see which one is must be true. Card number 1 is not in box Q. Actually, the card number 1 is always in box Q, so that one's definitely false. 4 cards in box Q have even numbers on them. In the first case here, only 3 have even numbers on them, only 1 in the second, and only 3 in the last one. So again, it's actually never true. So we're looking for something that's always true. Card number 5 is in box Q. Well, the card number 5 is sometimes in box Q, but in the last option here it's not, it's in box P. So you could get caught out in this question if you just like found one option and said, ah, yeah, okay, 5 is in box Q. But actually, if you did do that and you looked at all the options, you should also notice that 2 is in box Q. So you shouldn't be able to confidently say, or to think it's C here. You might be able to think, oh, it's maybe C or D. Anyway, 5 is not always in box Q, but you can see that 2 is always in box Q. And so actually the answer here is D. And again, exactly 3 cards in box Q have odd numbers on them. Again, that's not true. In the first case, there's only 2 odd numbers. In the next one, there's 4. And in the last one here, there's 2. So that's actually never true again. Anyway, the answer here is D. In question 17, it says the diagram shows a square, an equilateral triangle, and a regular pentagon. What is the size of angle WUV? Now, WUV, I've just made a bigger copy of the diagram again. The awkward thing here is it's not one that's already on the diagram, right? So I actually need to add in an extra line here, and then the angle that we're looking for, WUV, is this one in here. Remember, it's always over the middle letter. Right, so what can I say here? We've got an equilateral triangle and a regular pentagon and a square. So the thing we know here, and this comes up a lot, is that all of the side lengths in this diagram are the same. So it's a square, so all of these sides are the same length. It's an equilateral triangle, and the equilateral triangle shares a side with the square, so all of these are equal as well. And the pentagon shares a side with the square, and it's regular, so all of these are equal as well. So I've got every line, apart from the one that I've drawn in, has the same length. So we know in an equilateral triangle the angles are 60 degrees, and in a square all of the angles are 90 degrees. So I've got 60s in here. Also in a pentagon, we know the exterior angle is 360 divided by 5, which is 72, and so the interior angle is 180 minus 72 is 108. Again, I talk a lot more about these sorts of things in this full Go for Gold in Maths Challenges course, but my interior angles here are 108. So we can put all this together, and look, this one here is 108, and then this one here is the difference between the 90 from the square and the 60 from the equilateral triangle, so that's 30. So if you think about this triangle WVU, the angle here is 108 plus 30, which is 138. Okay, that's just a copy of VUW. But the other thing we know is that this side is one of the sides of the equilateral triangle, and this is one of the sides of the pentagon, and we said they all have the same length. So this is an isosceles triangle. Right, so that means that these two are the same, and so I've got 138 plus 2x is 180, or 2x is 180 minus 138, which is 42, and so x is 42 divided by 2, which is 21 degrees, and so the answer is A. In the diagram, spade, diamond and club each represent a positive integer. The sums of the numbers in each row and each column are as shown. What's the value of spade plus diamond minus club? So let's just call these X, Y and Z for spade, diamond and club. You could use S, D and C if you want to, but the S looks a bit too much like a 5 and the D looks a bit too much like a 0 for my liking, so I'm going to use X, Y and Z. So effectively here what we want to work out is X plus Y minus Z. And if we look at the information we've been given, all of these rows that are 47 and this column, they basically all have one of each of the symbols in them. So we're told that X plus Y plus Z is equal to 47. And the other information I've got this row on the top as 53. So that's 2x plus y is 53. For this column here, I've got x plus 2y equals 52. And for this last column here, I've got that 2x plus z would be 48. So we've got lots of equations here, and these are effectively simultaneous equations, and there are many different ways you can solve them. You can try substituting them in different ways, playing around with them, working out what the difference between them is and things like this. So I'm just going to show you one way of doing it here, which is that you could take these two, which corresponds to this first row and this first column, and add them together. and that would give you 3x plus 3y is equal to 105. And this is nice because it allows us to, because it's symmetric here, we've got 3x and 3y, I can divide the whole thing by 3, and I can find that x plus y is equal to 105 divided by 3, which is 35. Okay. At that point, we can remember in the first one, x plus y plus z is 47, right? So, but I know x plus y, which is 35 now, so I can say 35 plus z is 47, and so z is 12, which is the club. Right, so actually I don't need to work out what x and y are individually here, because the question asks me what's x plus y minus z, so x plus y is 35, z is 12, so I do 35 minus 12, and I get 23, and there we have the answer is E. Of course, once you've got z, you can also easily work out x and y here as well if you wanted to. We just don't need to for this question, right? So if z is 12, then I'd have 2x plus 12 is 48, so 2x is 36, and x equals 18. And then once I've got that, I could work out y as well, because I know that x plus y is equal to 35, so it must be that y is 35 minus 18, which is 17. So we don't need to do the bit in green, but there are other ways that you could solve these equations that might lead you to work out x or y first rather than z or something, which would all be valid. Anyway, whichever way you do it, if you haven't made a mistake, you should get that the answer here is E, 23. In question 19, we've got PQRS is a square of side 10 centimeters, and the distance MN is 6. Again, I've got a bigger picture of the diagram here. So this is 6 centimeters along, but the whole square is 10 centimeters along. And then it says it's divided into 4 congruent squares. So that's these 4 here. 4 congruent isosceles triangles, here, 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 and here, and the shaded region. And we want to know what the area of the shaded region is. Right, so firstly notice by the symmetry here, or the fact these two squares are congruent, the total of their side lengths has to be 10 minus 6, which is 4, so individually they must be 2 centimeters each, so we know the size of the squares. And this question really, by the way, is one that we should be thinking about doing by subtraction here, rather than working out the parts of the shaded area individually, although maybe you could do that. It does seem quite natural here to think of the shaded area as the big square, which is 100, 10 by 10 square, minus 4 of these small squares, and we know their area 4 now because we've just seen that they have side length 2, and then I need to subtract 4 times the triangles, right? So all I've got to do here is work out what the area of these triangles are. Now, okay, so they're 6 centimeters across, and the key to this question is actually realizing that this is a right angle. Now, for the maths challenges, you might look at this and say, it's a right angle triangle, it's like obviously a right angle triangle, without thinking about it too much, and you can get away with that here. It turns out to be right. You should be, perhaps in the back of your mind, worried, is it really a right angle triangle? It definitely is, because, for example, if you think about this triangle here, we know, because these triangles are congruent, that this has to be an isosceles triangle. So this is 90, and then this would be 45 and 45, and because we're told these smaller triangles are isosceles as well, that must be 45, and so that must be 90, so it does work out, right? Now, let's just think about these individual triangles then. We'll do this in 2 ways. So this length is 6, this is a right angle, and we've got side length of x here. So the area of this triangle would be half base times height, which would be a half x squared. Now, Pythagoras' theorem tells you that when you do x squared plus x squared, you get 6 squared, which is 36, so 2x squared equals 36. Now, you might just be doing the kangaroo without having done Pythagoras' theorem. Some schools might not teach this until a bit later on. If you haven't done Pythagoras' theorem, I'll show you another way of doing this question in a second. But Pythagoras, I think, is, for the kangaroo, something that could be useful, even if it's not absolutely necessary here. And so if I divide by 2 here, I get x squared equals 18, so x would be the square root of 18, but I don't actually need to work that out here because all I want is the area, which is a half x squared. So I divide that by 2 and I get 9. So actually these 4 triangles are all 9 centimeters squared. So the shaded area that we were working out here is 100 minus 16 minus 36. 36 plus 16 is 52, so that leaves us with 48 centimeters squared, and so the answer here is C. Now the other way of doing this, which is quite sneaky without Pythagoras theorem, is actually to say you could take these 4 triangles and you could put them together to form a square like this, and sort of push them in sort of from the sides and from the tops, and I'm sort of imagining just pushing them all together like this, right, and then forming this square, and that would be a 6 by 6 square because the side lengths are 6, so that would get us that 36 that we got here in a different way as well, and then you could subtract it in the same way. Okay, so tricky little question, that one, but the answer is C, 48. Right, in question 20 it says the diagram shows a 2x4 table in which the numbers in each column except the first column are the sum and the difference of the numbers in the previous column. Carl completes a 2x7 table in the same way and obtains the numbers 96 and 64 in the final column. What is the sum of the numbers in the first column of Carl's table? So first just check you really understand how this works. So it says the numbers are the sum and the difference of the numbers in the previous column, right? So if I take 10 and 3, right, 10 plus 3 is 13, and that gives me this number, and 10 minus 3 is 7, and that gives me this number, right? And I keep doing that through the table. Okay, so I then do 13 plus 7 gives me 20, 13 minus 7 is 6, 20 plus 6 is 26, 20 minus 6 is 14. You might also just stop and pause and say, can you see any patterns here as well? And like 10 and 3 is exactly half of 20 and 6, and 13 and 7 is exactly half of 26 and 14. And you might just think, oh, is that something that happens in general? So we're going to look at this in a couple of different ways. It says we've got a 2x7 table, and 96 and 64 end up in the final column. I want to work back to the first want to work back to the first column here. Okay, so imagine the previous 2 numbers were x and y. Okay, so right, so let me just make sure I'm being clear here. Right, I'm trying to fill in this table from right to left effectively. It's got 7 columns, so we need to go all the way back to work out what the numbers here are. But if we start, even though it might take a while to begin with, we'll find a way of speeding it up as we go through. Right, so I need x plus y to be 96, and I need x minus y to be 64. Okay, so I've got simultaneous equations here. I can add them together to get 2x equals 160, and the y's cancel out, and I could subtract the simultaneous equations, and then I'd have y minus minus y is 2y, and the x's would cancel out. And here I'd get 96 minus 64, which is 32. So dividing by 2 here, I get that x equals 80 and y equals 16. By the way, if you haven't done simultaneous equations or you're not comfortable with them, by the end we'll have another way of doing this that doesn't necessarily need them as well. Okay, you could just basically spot this thing about the doubling that I mentioned. But this is a really interesting method in general, right? Because how can I extend this to sort of work out the rest of this table pretty quickly, right? I now know that the x and the y here are 80 and 16, but I'm going to have to do this many times, right? Well, if you think about the formula we've ended up, imagine we didn't ended up with here. Right? So imagine these were just any other numbers, right? I could replace the argument with 80 and 16 and sort of make this the new x and y, right? But let's just say they're numbers, that these numbers are, a and b. Right, and I want to work back to x and y. Adding these together, right, I find that 2x is a plus b, and subtracting them, I get a minus b. Right. Previously we had a plus b was 96 plus 64, and a minus b is 96 minus 64. Right. So sort of in general for this formula, right, we get a plus b over 2 and a minus b over 2. So actually, to go back a step in this table, all I have to do is add the numbers together and divide by 2, and subtract them and divide by 2, and that will move us back through this table, right? So 80 plus, I can do 80 plus 16 is 96, divide that by 2 and I get 48. Whereas 80 minus 16 is 64 divided by 2 is 32, and I keep working back. Do the same thing again, add them together, and I get 80 divided by 2 is 40, subtracting them I get 16 divided by 2 is 8, and notice this thing with the doubling is happening again, right? 80 and 16 is double 40 and 8, so you could possibly shortcut it now and just say, okay, if I see this is just a doubling sequence and I think that's really true, I could say this one's going to end up as 20 and 4, and in fact I could halve these ones and say this one's going to end up as 24 and 16, and halve these again and say it's just going to end up as 12 and 8, and you really can just go back through and check that works there by following those numbers through. I'm not going to do every single one. That is what we end up with. We end up with 12 plus 8 being 20, and the answer is B. If you want to be confident about this doubling thing as well, just start with two numbers x and y at the start of the table, add them together to get x plus y and x minus y. Okay, and now for the next column, if I add together x plus y and x minus y, I get 2x, and if I subtract them, x plus y minus x minus y, the x's cancel out here. That's not very neat. The x's cancel out and the y's combine to give 2y, and that really does prove that if I keep following this rule that I double from here to here. Okay, but I think that's a bit hard to see kind of straight away, so well done if you did, but I think sort of a lot of students' first instincts will be to try and do something like I've done here. Maybe you spot the doubling at some point as you're going along. If you do, you can save yourself some time. If you're going to do all these questions in an hour for the Kangaroo, you're going to have to spot some of these things, but of course it's meant to be incredibly tough to get anywhere near all of the answers in this paper. If you get just some of these right, this is already the second round of the competition, so if you get even some of these right, you're doing very, very well indeed. So I really hope that was useful. If you're preparing for maths challenges, either the Junior Maths Challenge or the Kangaroo or the Olympiad papers, don't forget about my online courses. I'll put the link in the description below. There's free courses there at the moment working through the Junior Maths Challenge from 2020 and 2021 with hints and solutions, and there are other courses about the Junior Maths Challenge and preparing for maths challenges over there already, and over the coming months and years I'm going to be making a lot more content as well, so sign up for the mailing list if you want to know about that, or keep checking back here on YouTube or over at the Mathsaurus website.